All right, so where we left off on Wednesday was we had discovered that I had made a mistake somewhere in my solution, and I told you that I would find it. Actually, it was much easier to find than I anticipated. Literally, the first step I took in setting up my differential equation contained the error. So if you look at the directions that I have the arrows drawn here, I had the current flowing in plus the current flowing out was equal to 0, when I should have had the current flowing in was equal to the current flowing out. So what I've done is I rewrote my expression with the current flowing in this direction, effectively just changing the sign on the first term, and that sign change trickles through, and we wind up having plus signs in our alpha equation and our beta equation where we used to have minus signs. From that, we find that alpha is 50.083 nepers per second, and omega naught is 7.071 radians per second. Since alpha is greater than omega naught, this was an overdamped system. I used our two values for alpha and omega naught to recalculate S1 and S2, and then put those values into our systems. And I found that A1 was negative 279.669 milliamps, A2 was 1.408 milliamps. And when I simulated those results using the new values for alpha, or the new values for S1 and S2, my simulation exactly matched the analytical solution. So that one minus sign that was a mistake at the beginning was enough to derail everything. So I cannot emphasize how important it is to be very meticulous about the algebra and things like that that you're doing in setting up these second order differential equations. It is very easy to make a simple mistake that will cause your results to be wrong and introduce a lot of frustration. So just wanted to fix that for you guys. Now we are going to talk about, let's get through all this stuff. We're going to look at a problem that contains two inductors and see how it behaves. So our circuit of interest for today is this guy, where we have some source voltage Vs, a switch that is closing at t is equal to 0, connected to some resistor R1, and we're going to have an inductor L1 here. A resistor R2 here, and an inductor L2 here. I'm going to define my quantities of interest. So we're going to have a voltage drop over inductor L1, a voltage drop over inductor L2, current flowing through inductor L1, and a current flowing through inductor L2, like so. And our goal here will be to get a differential equation of the form, the second derivative of IL1 plus B times the first derivative of IL1 plus C times IL1 is equal to some constant value K, or the second derivative of IL2 plus B times the first derivative of IL2 plus C times IL2 is equal to some constant value. If we can get a differential equation or second order differential equation, either in terms of IL1 or in terms of IL2, then we can apply our relationships where we know that alpha is just going to be B over 2 and omega naught is just going to be the square root of C. And from this point on, we can treat it as if it were any plain Jane second order differential circuit. So for t greater than or equal to 0 plus, our circuit is going to look like this. Our voltage source is on, our switch is closed, so I'm just going to draw resistor R1 connected directly to our voltage source since our switch is acting like a short circuit. Here is inductor L1. Here is resistor R2. And inductor L2. Here is our voltage, VL1, our voltage VL2, current IL1, our current IL2. So the first thing I'm going to do here is I'm going to apply Kirchhoff's current law at that top node. I'm going to say that this current plus this current plus this current is equal to 0, and I'm going to try my damnedest to not make a mistake with the signs today. So applying Kirchhoff's voltage law around the left-hand loop tells us that the voltage drop over resistor R1 is going to be VL1 minus VS, and we're going to divide this by R1. Then we have our current flowing down, which is IL1, and then we have our current flowing to the right, which is IL2. Set this equal to 0. I'm going to move my constant term to the right-hand side, and I'm going to express the voltage drop across inductor L1 in terms of the current flowing through inductor L1. That's going to look like L1 di L1 dt plus IL1 plus IL2 is equal to VS over R1. And I've actually already made a mistake, so I'm going to go ahead and fix it now that I've noticed it. When I did my conversion, changing VL1 into LDI by dt, I forgot to that there was also a factor of 1 over R1 that I needed. So I'm going to write this as L1 over R1. Just to be very clear, this R1 is coming from here. Okay. All right. Now I'm going to write Kirchhoff's voltage law equation around the right-hand loop. So my KVL equation is going to look like, so let me be specific about what I'm doing here. I'm going around this path. So I'm going to have negative VL1 plus the voltage drop over my resistor R2, which is going to be R2 times IL2, plus the voltage drop over my inductor L2, which is VL2. I set this equal to 0. And what I'm going to do now is I'm going to move my VL2, or excuse me, my VL1 term to the other side of the equal sign. So that's going to give me VL1 is equal to R2 IL2 plus VL2. I'm now going to express both of my inductor voltages in terms of the inductor currents. So this is going to tell me that L1 DIL1 is equal to L2 DIL2 by dt plus R2 times IL2. And now I have to make a decision here, okay? So this equation that I just wrote from my KVL relationship expresses the derivative of inductor current IL1 in terms of the derivative of inductor current IL2 plus the current IL2, including some coefficients here, right? Well, my goal is to make a second order differential equation. So I need to figure out how I can do that. If I look back at this first equation, so let's put 1 by it, we can see that I can do a little bit more manipulation that would allow me to isolate IL2 is equal to some function of IL1 plus a constant. So I'm going to do that. Call this guy right here, equation 2. So as I said, I'm going to algebraically manipulate equation number 1. So I'm going to have IL2 as a function of time by itself. So that's going to be Vs over R1 minus L1 over R1 DIL1 by dt minus IL1. Let's call this equation 3. And now what I'm going to do is I'm going to take the derivative of this guy because I need a derivative of IL2 equation to plug into equation number 2. So the derivative of equation 3 with respect to time is going to look like d IL2 by dt is equal to, so the derivative of our constant term is going to be 0. Then I'm going to have the derivative of negative L1 over R1 times the first derivative of IL1. So when I take the derivative of that, it's going to look like the second derivative. And now I'm going to have minus the derivative of IL1. So minus d IL1 by dt. Let's call this equation number 4. And now I can simply plug equations number 3 and number 4 into equation 2. So write that down. Substituting 3 and 4 into 2 is going to give us L DIL1 is equal to L2. Now I'm going to substitute in equation 4. So that's going to look like negative L1 over R1 times the second derivative of IL1 minus the first derivative of IL1 plus R2 times IL2, and this is where I'm going to substitute in equation number 3. So I'm going to have Vs over R1 minus L1 over R1 times my first derivative of IL1 minus IL1. And now what I'm going to do is simply move all of my IL terms to the left-hand side of my equal sign, okay? So I'm going to have to kind of go back and forth between this screen and the next because I ran out of room here, but that's going to be okay. So the first thing that I want is my second derivative term. So I can see that on the right-hand side of my equal sign right now, I have a negative L1, L2 over R1 times my second derivative. When I move that to the left-hand side of the equal sign, that's going to look like positive L1, L2 over R1. So let's put that here, L1, L2 over R1 times the second derivative of IL1 plus, now let's go back and look at our first derivative terms, okay? So on the left-hand side, I have a factor of, I wrote L, this should be L1. On the right-hand side, I have a factor of L2. And I also have a factor of R2 times L1 over R1. So when I lump all of those terms together and move it to the left-hand side of the equal sign, that's going to look like L1 from this term, L2 from this term, and then L1 times R2 over R1 from this term. R2 over R1. D IL dt. And now I'm going to have whatever is being multiplied by just IL1. So let's look at our 0th derivative terms here. So the only time that the 0th derivative shows up, unless I'm missing something, is this guy right here. I don't see any other IL1s that don't have a derivative associated with it. Well, that term is multiplied by a factor of R2. When we move it to the left-hand side of the equal sign, that's just going to look like plus R2 times IL1 of T. And the only term that's left, let me scroll down to the bottom here, is, I believe, this constant term right here, which is just going to look like Vs multiplied by R2 over R1. Over R1 times Vs. Since we want the coefficient on the second derivative term to be 1, that means we're going to have to divide through by L1, L2 over R1, which is the same as multiplying by R1 over L1 times L2. So from that, we're going to get the second derivative of IL1 plus R1 over L1, L2 times L1 plus L2 plus L1 times R2 over R1. Our first derivative. And we're going to have R1, R2 over L1, L2 times our 0th derivative. And now we're going to have R2 over L1, L2 times Vs here as our constant term, right? Because the R1 in the numerator is going to cancel the R1 in the denominator. We can now see that this bit right here is our coefficient B. And this bit right here is our coefficient C. So alpha, which is B over 2, would be given by 1/2 R1 over L1, L2 times L1 plus L2 plus L1 times R2 over R1. And omega naught, which is the square root of C, would be given by the square root of R1, R2 over L1, L2. So my question for you guys is, do you want to throw numbers into this to see how the circuit behaves? Or are we good at this point now that we've calculated or we've determined alpha and omega naught? And at this point, we're just doing the exact same thing we've been doing for the last 2 weeks. All right, let's see the chat. All right, skip the number crunching. That was where I was going to get to as well. I believe we've beat that part of the problems to death, and I've asked you to do it multiple times in your homework sets and on your exam and all that kind of good stuff. So that's really all I wanted to introduce for today. Just an example of a problem that contains two uncoupled energy storage elements of the same type. If you have any questions about anything, I will be available the majority of the weekend, as well as the July 4th holiday, I guess, which we're observing Monday. Yeah, because that is actually the 4th. So if you have any questions about anything, I would be happy to answer them. I do want to check something just really quickly on the syllabus. All right, so we don't have class on Monday because it's the Independence holiday. Your exam 2 is effectively given on Wednesday. It's been up for several weeks. I don't intend for us to actually have a class on Wednesday morning. However, I will be here and I can be available on Zoom if anybody has any questions. So effectively, you've got the remainder of today, tomorrow, Sunday, Monday, Tuesday, and all day Wednesday to wrap up these homework assignments and get that exam in, and I'm free pretty much this entire time if you have any questions. So do not hesitate to reach out either via email. Some of you might have my cell phone number. However you choose to reach out to me, go nuts and I'll get back to you as soon as I'm able to. Hope you all have a happy and safe Independence Day holiday, and I will see you it looks like 1 week from today when we start talking about steady state sinusoidal analysis, if you don't have any questions to ask me before then.